So much of our modern technology has been driven by improvements in our understanding and ability to control and manipulate materials. So we mentioned silicon. So of course silicon is the heart of all our computer chips. We can now make this incredibly pure. We can control it at the nanoscale. We can make new fabrics and devices that are a few atoms across. We're getting to the stage now where to make the devices smaller and faster, we're getting to limits where quantum effects start to dominate. And the wires are now a few atoms in size, and classical ideas of electrical conductivity and wires and resistors and capacitors just break down at the quantum scale. So some people are looking at new materials that might replace silicon in the future. So one of those is graphene. So graphene is the wonder material that you might have heard of, and it's a sheet of carbon atoms that's one atom thick. So this is a kind of schematic model. I can't hold a piece of graphene and show you, it's too thin to show, right? But this is the kind of the crystal structure. So the black blobs are the carbon atoms, and the green are where the bonds are. It kind of shows you the crystal structure of a single sheet of graphite called graphene. And graphene is interesting because it's ultra fast in the way that the electrons move across it. They have a new quantum state, and so for that reason people are interested in, can they use graphene as a new material for making computer devices out of that could be ultra fast in the future. People have been doing that for a few years, and that's fairly well understood. What I'm more interested about is what happens when you take your sheet of graphene and start cutting it up. If you have an infinite sheet of graphene, it has these wonderful properties. But when you start machining it and cutting it to make a device, to make a wire, then you find that it's no longer quite as good. So depending on how you cut it, you can either have an edge like this, we call that the armchair edge, or an edge like this. I'll just take those off, that's from a different calculation. Oh dear, it's all gone disastrous. This is called the zigzag edge. So if you imagine you've got a wire going along like this, if you've got a zigzag edge, that edge actually changes the properties of the wire compared to if you've got an armchair edge. Because it's so small, it's only a few atoms across, that the different structure of the edge affects the electrical properties of the wire. So try and understand that and why that might be. So when these materials were first studied theoretically, they started looking at the properties of these edges, they came to the conclusion that this edge here, the zigzag edge, could be magnetic. And suddenly we see magnetic carbon, kind of, who ordered that? Where's that come from? And maybe we could use this with that other stuff I was talking about, with the spin, to make a spintronics device, to make something that could be a wire. Well, it turns out the theoreticians who were doing the calculations were a little bit over-optimistic, and they only had idealized perfect wires. And once they started putting a bit of rubbish and a bit of imperfections into material, or a bit of extra gas, like a bit of hydrogen comes along, and a hydrogen atom comes along and it sticks on this edge, then that is very, very effective in killing the magnetism of this edge. So in real materials exposed to air, gas, these things don't happen. So for the magnetic properties, graphite or graphene is useless. However, that got people thinking, are there other materials we can make that are two-dimensional as well? Materials that in the bulk form are these layered compounds, can we peel off one layer of those as well? And so I've joined a group of people who've been studying these materials, and the material we're looking at the moment is called molybdenum disulfide. It's a little bit more chemically complicated. It's been around in the automotive industry for years as liquid moly, as a high-performance engine lubricant. But they suddenly discovered that the reason it's a good lubricant is it's easy to rip off these sheets of atoms, and that's how it's easy to make a two-dimensional sheet of the material. And with that material, we believe you can make it magnetic, and you can actually preserve the magnetization, and you can actually make a device out of it.